Okay, well, good morning, everybody. Thanks for coming to the inaugural Fog Computing Conference. Thanks to Carl for all of his adventures in putting it together. Cisco decided that we were going to step up to the highest sponsorship level of this conference because we really think that fog computing is an important future technology that's worth everybody's close attention. So what I'm going to try to do for the next half an hour or so is describe exactly what Cisco thinks fog computing is. And there will certainly be a few things in my presentation that you will resonate with. There will certainly be a few things in my presentation that you will find argumentative or even plain out incorrect. And I think we're at the stage of this whole industry where that kind of dialogue is really interesting. So don't expect that all the answers that you're going to see from myself or my three fellow Cisco speakers are going to be fully baked and completely Cisco policy. Much of this is a work in progress, but it's a work in progress that's sufficiently progressed that I think it's worth sharing with you folks. So let's dump into the presentation here. Oops, too many goes. My talk starts with a little bit of information about what's going on in the Internet of Everything, which is Cisco's marketing term for the Internet of Things plus plus. And we'll talk a little bit about what that is. And the key portion of my talk is, why can't I just do everything with a smart sensor or actuator in the cloud? Why do I even need this layer of fog in the middle? Once we collectively understand why you can't just do it in the cloud or you can't just do it in smart actuators, you really need this hierarchy of connectivity, I think that we'll be on a good road to understanding what fog should be doing for our industry. So the bulk of my talk is why you can't do it all in cloud and why you can't do it all in smart devices. Here's the agenda. So some marketing slides on IoT. I promise I won't bore you for more than 5 minutes on that. Talk a little bit about architectures and how the IoT is evolving. Talk a little bit about the properties of what we call fog nodes. Those are the physical engines sitting in the fog providing these services. And why we don't think that we can necessarily build simplistic IoT, endpoint, and cloud-only models. Why the fog matters. So that's the bulk of the talk. This is Cisco's IoE slide. So we took the IoT, as we all know and love, and we've decided that it needs to be more. The real value isn't just things, it's these four elements all networked together, high speeds, high security, high application integration. So the first thing is people, and certainly people are the reason we do this. There may not be any people in the loop of a pure M2M play, but somebody gets a report on how that automated system works, and those people need to be forefront in the loop. We talk a little bit about processes. So the right information to the right people or the right machines at the right time is very important to keep the internet flowing smoothly and to avoid tons and tons of potential problems that could occur. Data is the currency of the Internet of Everything. And we want to have lots of information flowing freely through it, but not so much information that everybody just gets bogged down by these big fire hoses. So data's got to be treated carefully in a hierarchical approach using many of the more modern techniques, big data, Hadoop, so forth. We'll be talking a little bit about those as the day goes on. And then finally, there are the physical things: sensors, actuators, mobile devices, routers, switches, servers. All these things are the most important parts of the IoT. The Internet of Things in general and fog computing specifically can serve many different vertical marketplaces. And I've given a smattering of them here, certainly not an exhaustive list. There are certainly things that have been in process with distributed intelligence and in some cases distributed storage and networking for 20 or 30 years. In fact, one could argue that the telephone network invented by Alexander Graham Bell was a distributed sort of fog-like system because there were things out in the field that did real work. So I don't know if we can claim that fog is a purely new concept. But I think the application of it to IoT and the rigor that we're going to bring to it with our descriptions throughout these 2 days, I think will show that there's something special going on that's beyond what's known in the current state of the art. So just a couple of verticals. I'm going to just shout out some of my favorites. Connected energy, smart grid kinds of applications. Certainly defense is an interesting thing. Lots of hierarchy and resiliency is necessary in that. Smart cities are huge. Rodolfo is going to talk quite a lot about our work in smart cities. Smart transportation, especially smart highway systems, parking space identification kinds of applications. Lots of things in the railroad and shipping industries also. So those are some of my favorite verticals. Some of the most interesting things that happen are in the interstitial spaces between those verticals. So, for example, transportation meets energy, and we might put a fog node mobile on a mining truck, for example. And the whole fully interconnected grid, I think everybody could think of places where fog is valuable across multiple verticals and in the spaces between verticals. Cisco does lots and lots of market research. If anybody's not familiar with the Cisco Visual Networking Index, or VNI, I suggest you do some web searches and spend an hour with it. A really interesting read. Statistical depth beyond belief, describing the future of the internet in general, and there are sub-chapters in the VNI related to the Internet of Things. When we think about the Internet of Everything, we come up with some staggering value propositions. These are 10-year numbers for 3 types of predominant communication that we find in the Internet of Everything. So there's machine-to-machine, that's automatic systems, automation of oil refineries, and those sorts of things. $7.4 trillion over that 10-year span. Yeah, that's trillion with a T. Machine-to-person is sort of every web app and everything that feels like a web app, and everything associated with every button that you push. That's $4.5 or $5 trillion. And then person-to-person is the multiple communication modes, collaboration, cell phones, standard communication networking, $7 trillion. So these trillions include all the bills that we pay to AT&T and Verizon, and all the bills that our machines are going to be paying to AT&T and Verizon, and all of the bills that we're going to pay all these app providers that are providing the value to those bits flowing on the network. Do the math, add those up, you get $19 trillion over 10 years. So that's a significant piece of money. I saw that and I said, there's no way. It's just impossible. 19 billion I could believe, 19 trillion? Really? And if you dig really deep into the numbers, yes, it's credible. There are really ways that this marketplace, over the span of those 10 years, are going to generate that kind of change. So that's why we're interested in working on this. That's why Cisco's sponsoring the conference and having all these people here today, because we believe that this market is real, and we believe that the fog subset of this market is very significant, multiple billions of dollars. Okay, I mentioned data flowing up and down the Internet of Things, and that's important. And the data gets more important as it gets more refined. This is what's sometimes called the DIKW model. Data begets information, begets knowledge, begets wisdom. And the source of much of the data on the IoT are these sensors and actuators that are distributed all around the globe. By one count, there's going to be around 50 billion of them by the end of the decade. And that's roughly 6 or 8 times the number of humans on the planet. So there's a significant amount of endpoints that are required. And by the way, that significant amount of endpoints, that scalability of the number of endpoints is one of the reasons why Cisco is so gung-ho about the conversion of IPv4 to IPv6 to get that blown out address space. Anyway, as you go up this hierarchy, every bit of information becomes more distilled, more concentrated, and more valuable. So it's like, beer, whiskey, cognac, maybe. I'm not sure. But anyway, what we end up with is ones and zeros flowing on raw physical layers. And then we end up with information about trends and aggregation of sensors and that kind of thing becomes information. It becomes usable as opposed to just ones and zeros. And then we apply some heuristics to that, and we get some knowledge. And that knowledge might represent trends over long terms or the physical state of a plant or the value of a particular device or whatever. And at the pinnacle of this is wisdom. And that is the application of everything below it to making good business decisions and safety decisions. The business benefit goes up as we go up that triangle. And the actual number of bits, the size of disk drive that you need to hold them, shall we say, it funnels down. So actually holding wisdom, it just might all boil into one particular spreadsheet that you mail to your CXO. But GE says jet engines make terabytes worth of data per hour of operation, right? So there's lots of work to be done to funnel up the DIKW model. Each of those red bars there represents an opportunity for fog computing. Let's talk a little bit about the cloud, which is one of the fundamental reasons why fog is named what it is and how it works the way it does. The cloud is basically an amorphous thing that's a bunch of servers in a data center somewhere, and it's talking to a whole bunch of devices, and you can see there's icons for computers and phones and cameras and all kinds of stuff. That's sort of today's model. When we go to the Internet of Things, we just blow out the number of devices, and the amount of traffic going around that network goes up by maybe 2 or 3 orders of magnitude over the coming decade. That traffic is going to cause some scalability problems on the internet. We're not going to be able to grow routers and links fast enough to haul all of the traffic from all of those 50 billion sensors into the cloud. We'll just bog the whole works down and nobody will get any work done. So here's some of the problems that we envision with this model of hauling everything to the cloud. There's just too much data. The fire hoses are too big. And it's latency is a little high. You'll hear Cisco harp about latency pretty much continuously because it might take a couple hundred milliseconds round trip from a sensor to a cloud-based decision maker to get to the top of the queue so the cloud does something, and then to go back down to an actuator. To close that loop is a couple hundred milliseconds. Many kinds of control systems go completely unstable in that scenario, and therefore the fog is necessary to help with that latency. The transport costs are too high, especially if there's satellite links or 3G cell phones that I only get 10 gigabytes of data. That's going to be really expensive if those fire hoses are running continuously. And we need something to bash that down in the middle. And finally, there's this question about resiliency. If there's a disaster or if a distributed denial of service attack completely overloads a cloud wire center, there's no way to determine. Let's just say that you can't distinguish a ridiculously slow network from a completely failed network. And fog can help us with some of that. So let's see what fog does. It puts this intermediate layer of stuff between the cloud and those endpoints. And we're adding a bunch of fog nodes. Those are the physical implementations, the manifestations of fog. And there's big ones and small ones and medium-sized ones, and some a little closer to the edge and some a little closer to the cloud. It's a hierarchy. And the point is it's very ad hoc, it's very grow as you need to, very topologically amorphous. And that's an important strength of cloud because it really helps us share the load, add resiliency, manage security, and many other things. If we do that configuration correctly, as defined by all those little 4-point stars, we can offload the cloud with those fire hoses of bit streams to the point where everybody gets some work done and the performance is adequate for real-time tasks. Talk a little bit about some of the basic properties of fog. We think that we need scalability on lots of different dimensions. That's one of the things that cloud might not do for us in a pure play is scalability. And scalability might be the kinds of applications we can run in addition to the sizes and numbers of applications we can run. And an important part of this is we need some cloud-like properties for fog. So we need virtualization, orchestration, multi-tenancy. And we also talked about the hierarchy and different kinds of modularities that might be necessary in order to equip exactly the right levels of fog functions at exactly the right levels of the network. Strong security is absolutely essential. Don's going to talk about this for an hour this afternoon. And strong security is really helpful and essential, necessary, because the consequences of security breaches, data breaches, hacking, overload attacks, they get much more severe in many Internet of Everything deployments. So it's one thing if Target has a data breach and maybe some credit card numbers get out into the wild. It's a completely different thing if I am running an autonomous vehicle on a smart highway and the roadside node gets hacked and turns all the vehicles to full speed. Lots of people are going to die. You'll see Internet of Things killing people by the end of next year. You'll hear about it. And it's grisly, but it's inevitable. Fog can help us with some of this. We also have this question of resiliency and fault tolerance. Is the network really trustworthy? And many of these applications have to go back to the old school telecom world of 5 nines kinds of availability. We think fog is highly programmable at multiple levels. So there are APIs that help us interoperate and program the functions in fog. We're supporting lots and lots of different applications through orchestration and virtualization, multi-tenancy, but those links between those applications are programmable. We want the operating environment to be very versatile, and Carlos will tell us quite a lot about that in his talk about how the software all makes this all fit together. And finally, there's real-time features. Deterministic timing is often, but not always, required, and the fundamental goal of Cisco's fog architectures is to allow arbitrary mixes of the 3 main types of resources that are necessary in these networks. And as you probably know, those are computation, networking, and storage. Put the right level of the right kind of processing, networking, and storage at the right place in the hierarchy in order to exactly meet the characteristics of the applied load of applications. We'll be the first to admit that cloud has similarities to systems that you already have seen deployed. Content delivery networks. There are people who talk about the hybrid cloud where edge data centers exist. Certainly intelligent edge devices like you might find in an access network or even a Wi-Fi AP with a processor in it that could be programmable. And there's many distributed branch models that do this. We think that we can articulate distinctions between all these existing models and Cisco's vision of fog, and we're going to attempt to do that over the coming 2 days. An important question in these hierarchical networks, this is a little different view of the one with the rings of clouds, sort of data center on top to sensors and things on the bottom. An important question is, where are the brains? And brains include those 3 types of functions of computation, networking, and storage. Where are they located? Well, we could put them all in the cloud. So everything below the cloud could be dumb. The sensors know how to dump data onto dumb pipes, and the information, knowledge, and wisdom is all gleaned in the central cloud. There are people who've tried that, and for a certain subset of applications, it might even work for a while. I don't think it's the right answer. We could also try to shove all the brains down into a smart device. So every sensor in the world could feel like iPhone in terms of its processing, storage, and networking capabilities. And it can make some autonomous decisions and maybe talk east-west to other smart things and probably implement some networking that would, and some IoE applications might just work that way. I don't think that's the final answer either. As you can probably anticipate, this is a fog conference. The final answer is a distribution of the networking, computation, and storage capabilities up and down this entire hierarchy. Sure, there's going to be things in the cloud that are working on information and wisdom layers. Sure, there's going to be some intelligence in the sensors and actuators that are just doing data and information processing. But the stuff that's working on the middle layers are distributed in the field area, things like intelligent gateways and programmable logic controllers, and the core and edge of the network, things like routers and service nodes of various kinds. when you get this fully distributed model where there's brains up and down this hierarchy, you have a lot of interesting toys in your sandbox in terms of application development and network design. And the fog, just to be clear, is sort of the stuff in between the two bookends there. That's where we sit on this hierarchical model. Go just a little bit more into some of the specific challenges associated with shoving the brains all the way up to the cloud or all the way down to the intelligent endpoints. Let's talk first about what problems we may face if we try to do too much in the cloud. Certainly latency is a big problem. We've identified applications at Cisco that will not work as expected if the latency is over about 1.5 milliseconds. That's a very tough thing to do. You can't even go more than a few hundred kilometers on a fiber at that, much less to a cloud data center in Iceland. If we have fewer network hops, lower focus loads, and lower network transit time with a local fog node, we can fix that latency problem. We think mobility is rather important here. And by data-rich mobility, we mean we want the nodes to be able to move around, especially for vehicular applications, but also human portable applications. If we locate the fog, the right data at the right levels of the fog, we can potentially do a much better performance, a much better data model, and we can also perform local caching functions in the fog, which helps the overall performance. Geographic diversity matters. Certain data can't be sent outside of certain geographies, especially sensitive government or military data. And we can localize the intelligence as appropriate in fog, so fog can solve some of those problems. Network bandwidth constraints are absolutely huge. If you're doing a connected vehicle application, you've got vehicle to infrastructure links of, if you're really lucky, a megabit, and that doesn't happen very often. If you're on a satellite link, the price is huge to get a gigabyte backhauled on a satellite. If we can get some local processing to reduce the amount of information that we have to send on expensive links, that's an important function of fog. Reliability and robustness is helpful. This is how we get to trustworthy computing and even up to 5 nines levels of availability. Fog can provide fast failover to adjacent neighboring fog nodes of the service logic. We can also completely respond locally in the case of an emergency. So for example, if there's an earthquake and all of the backhaul and internet links are busted, it's very possible that there might be a battery and a fog node at the base of a cell tower. And if I call 911, maybe that cell tower local processor can emulate small fractions of the 911 response center and maybe route my call to a local fire department or something. Whatever it can reach, it's going to try to do that. That's an important function of fog and something that I think we should all work towards applying. Analytics is really important. Analytics is the software that changes the data to information, knowledge to wisdom. And if we put the analytics and the storage for the data that drives those analytics at the right level of that hierarchy in fog nodes, we can really make that very efficient. We can optimize the amount of data that we're transporting, and we can optimize the response time, and we can optimize the accuracy and computational load. Certainly, user data and geographic privacy is an important consideration. So fog can anonymize, which I think is actually a real word, and aggregate user data, meaning that if a bunch of folks, say in a restaurant, they're pushing don't like the tuna sandwich, fog node could anonymize that and send you've got 18 customers that don't like the tuna sandwich to the chef of that restaurant without getting anybody particularly irritated with an individual. That's the sort of thing that fog can do, anonymity and aggregation of user data. Let's talk about the converse piece. What happens if we try to push too much intelligence down into the endpoint, sort of a Microsoft or Apple model where the endpoints are the thing that matter? Endpoints often have significant physical constraints. So my device runs on a watt or two, and it can only do that power level for a few hours. And if sensors, for example, using harvested energy or batteries, they may need battery lives of 10 years. I obviously have a problem with with putting significant computation power into the energy envelope that's available in those endpoint devices. Space is a big deal. I definitely, if I'm man portable, I've only got a few hundred milliliters of physical volume. I'm not going to put terabytes worth of disk drive into that. If I need terabytes worth of disk drive, I need to jump to the next layer in the hierarchy, and that's where the fog would be. Certainly environmental considerations are important. Certain types of computation, optics, and storage just don't like to live out in the elements. They'd like to be in something slightly more controlled. So for example, if I've got a bunch of parking lot sensors frozen under my streets where I come from in Chicago that are telling me what spaces are there, I probably can't put significant computation or optical networking into those sensors themselves because those sensors are just too cold or too hot for that electronics to survive. If I have a simple, robust radio link back to a fog node, that fog node can implement the full Xeon or AMD equivalent or ARM equivalent of that kind of processing and get a lot of work done in a way that's not environmentally constrained. So fog nodes can access more energy. They're probably grid connected. They could be on the end of a power over Ethernet connection, for example. They can be physically larger, street corner cabinets as opposed to something that would fit in a bicycle. And certainly better cooling systems can help with the environmental pieces. And it's not just cooling, it's mounting for vibration resistance. Lots of different things can be improved by backing the critical computation, networking, and storage functions further into the network. There's also some functional constraints on the endpoints that we have to be concerned about. Processor throughput. Most endpoints can't afford, for energy, space, and dollars reasons, to have enough processing power to do the kinds of analytics that we'd love to do. And running that information across to a fog node can help. Storage capacity, physical devices definitely don't have terabytes of storage. Fog nodes can. Reliability, some of those remote devices might not be completely reliable. They might not be physically secure. They might not have the kinds of capabilities for robustness and duplication that fog nodes could have. And then finally, there's modularity, where a simple, cheap device probably doesn't have opportunities to plug a lot of stuff on. So if I want different kinds of radios or different kinds of storage, the endpoint devices are typically not modular the way that fog would be. So we have architectures for fog nodes that are petabyte sized in terms of storage. That's very useful in oil exploration, for example. The seismic data structures are about that size. Fog capabilities can have more redundancy, optionally, and more modularity. Finally, there's this whole question about the endpoint security. What happens if an endpoint gets stolen or run over by a garbage truck or whatever? We think that fog is an opportunity to take the critical data and shove it a little bit further out of harm's way, or the critical processing infrastructure, shove that a little further out of harm's way. Okay, so that's hopefully a reasonably clear reason why the plus signs are advantages of putting the computation, networking, and storage capability at intermediate levels of the network hierarchy. On to the next steps. So this is, I think, what we need to do collectively in this room, is identify use cases where fog provides significant advantages. What verticals, what applications among those verticals. We want to refine our views of what fog architecture is. And fog architecture, I've laid it out at the highest level. And I think that looking forward in some of the presentations that are happening in the next 2 days, we'll come away from this conference with a much better view of what fog architecture should look like. And that's architecture at the high level, how it fits into the IOE, and even low-level architecture of individual fog nodes will be discussed. We think that we need an application architecture that facilitates interoperability, migration, programmability, multi-tenancy, all of that kind of thing. So it's necessary for us to understand how fog can be put to work by lots of different types of people doing lots of different types of application work with lots of levels of sophistication. There are application programming interfaces for fog, and everybody in this room should look them up, figure out which of them you like the best, and start experimenting with them. We'd love to see proofs of concepts and prototypes, and Cisco is interested in pulling some of those together. We'll hear a little bit more about those in the afternoon. One of the most important problems is the business models and the economic models associated with deploying fog. Putting all these little engines out there on light poles and street corner cabinets and in vehicles, it's going to be expensive. It's got to show value. In order to make it happen, it's got to have a compelling economic advantage. And I think that we can start collectively taking a look at those business cases and understanding where they're the most wildly positive, and that will help us focus our fog attention into those applications. I don't think we should limit our fog attention to the ones that come out as highly economically viable today, because there's lots of other applications that might be peripherally related or even completely unrelated that I believe will grow into very valuable applications for fog. So don't put your blinders on, but it's good to focus a little bit. And then finally, we are at the point right now, starting now and moving forward the next year or so, where fog deployment is in its infancy, but as any exponential, it's going to be a hockey stick. There's the end of my talk, and there's a URL for general Cisco Internet of Everything questions. Okay. Thank you, guys.